Welcome back, everyone. And now we're back with more intersections, but this time we're finally escaping the 2D world of intersections that exist within 3D. You know, you were doing the triangles, the quads, the circles, which everything required us to determine what plane these things existed in. Now we're going to move into more of a three-dimensional. And the bread and butter of intersections and collisions are something called bounding boxes. And there's actually two types of bounding boxes. One is called axis-aligned bounding box. The other one's called oriented bounding box. The difference between the two is that an object, axis-aligned bounding box, does not rotate. It stays static, aligned to the axis of the 3D world. Where the object aligned is the square or the cube that encompasses your object has the exact same rotation as the object that it's bound to. So here's like a Google image search of like examples of what a bounding box is. All it is just a square outline. And a bounding box is defined by two vertices, the maximum and minimum vertices. So it's like, so you have the smallest XYZ paired with the greatest XYZ. And that defines the two corners of a cube. So you can have the bottom back corner and then the top front corner based on what kind of system you're dealing. You know, DirectX and OpenGL, they have different orientation directions. But it's defined by minimum and maximum. And if you remember in the previous lessons that we're dealing with GTLF data types, the data files to load in models, if you remember correctly, one of the data that comes with model data is the minimum and maximum vertice. That is a pre-calculated data for us to actually create our bounding box for our objects. So if you're dealing with objects like that, all that information is already there for you. For loading in object files, you have to pre-calculate or you have to calculate your bounding definition yourself. So you have to go through every single vertice and determine the smallest and the maximum components for that. You maybe say, what exactly are bounding boxes or what are they for? Well, they're a quick, easy way to do collision or intersections with array. They just encompass the object that you're trying to basically touch in 3D space. They're like the starting point or the bread and butter of interacting with 3D space. You know, that's really the gist of what these are. Like, you'll have like more complicated bounding things. Like the simplest one is supposed to be a sphere. Then you have cubes, and then you have more complicated things like not a cylinder, but a capsule. A capsule is a cylinder in two spheres, so it's a more complicated thing you have to deal with. So and another thing about bounding boxes is, like, if you see this one image where you have one whole bound object, and then you have several little ones built inside to kind of subdivide. Let's see if I can open it up a little bigger. Oops. That subdivide the object a little bit further. The idea is that let's in terms of games, if you're doing, let's say, you're shooting a gun, right? And you shoot a ray through 3D space, and you're trying to find where you hit. The first thing you're going to do is do a simple AABB, axis-aligned bounding box intersection. So the first thing you're going to do is go through all the objects in the screen and find the first object you hit. So let's say you hit this object because it's that one bound box. Now, if you're doing like a shooter, like any kind of shooter really, and you want to do like headshots, then inside this bounding box, once you found this object, okay, this is the object I actually hit. Then you go and then do more detections inside. So then you check every single bounding box that's within that bounding box. So you can see, like in the case of a plane, you can say if you're shooting a missile, if you hit, let's say, this part of the wing, you can then animate that part of the wing gets exploded, that it gets destroyed. Or, if you hit, maybe if you have a separate bounding box just for the tail, that part gets destroyed, and then you see the plane crash. Same thing, like I said, with first-person shooters. You can put a bounding box around a person's head, a bounding box around their legs, around their chest, their arms. And depending on what part of the body that gets hit, you can treat it differently. Like, if the bounding box on the head is the one that actually gets the bullet shot or the ray shot, then you can instant kill the character. If you end up shooting the part of the leg, then you can say, well, you can make the character collapse on the floor, things like that. Or, if you shoot the arm, you can have the person drop the gun. So you can make it more realistic. Where if you can just do just a regular bounding box on the whole object, then you're just attacking the character. And that could be like good for an RPG game where you just hack and slash. So as long as you're within that box sphere and you're hitting the person with your weapon, that's good enough. So it really comes down to how specific how much detail or how granular you want your intersections to be. Do you just want to hit the object in general, or there's specific areas within the object that you're trying to hit? But at the end of the day, you're always going to check the bounding box of the whole object first when you're kind of looping through everything that's on the screen, just to find that one thing you actually hit. And then from there, then you do the secondary check if you need to, like especially for certain games that you're developing. So I think that's everything I can probably tell you about bounding boxes, right? So there's a lot of tutorials, especially Scratch a Pixel, which is a great site if you want to learn the mathematics of graphics programming. They try to show you how to do bounding boxes this way. And for some reason, I have a hard time visualizing this. For me, this took me a while to get it. I understand it now, but to me, it still doesn't make sense. So we're going to do this not in a flat world. We're going to do this in 3D. So I'm gonna try to illustrate to you this how it really looks in 3D space, instead of trying to see everything in a one-dimensional flat or two-dimensional world. So we don't need that anymore. We don't need that anymore. So we do have a bounding box now. Very simple, right? So if we go back to here, in entities folder in Fungi, you will find a new module called bounding box. The way it just extends the renderable, and I'm still playing around with it. I'm saving the min and max, but Scratch a Pixel had a really cool way to optimize speeding up the process of checking bounding boxes, and they set it up with saving it as an array, the minimum and maximum. And I experimented with something like this called bound flat, which I actually put everything in one large array. And it's actually I used this. I might end up just going into GenBox, because that's really used to make generating the box a lot quicker for me. But that's something I only need to call once. So I might end up moving that over to here. So this object's still in flux. I have like to-dos, telling myself maybe I shouldn't bother using my dynamic buffer. Maybe I should just use straight up VO buffers, or not use any of this stuff really at all. Just I've created other bounding objects that are simpler than this. So I'm just kind of trying to. I'm trying to create all my bounding objects, and then at some point, find out the simplest solution, and then have all the bounding boxes built the same way. So it's just really experimental. Feel free to kind of look through it, get an idea what's going on. But yeah, like a bounding box is defined by maximum and minimum. It's just a vec3, and like I said, there's many ways you can save the data. This way works pretty well. Based on optimization from Scratch a Pixel. This way, I think, works really well in terms of rendering. So this is more of a rendering thing, optimization for me. Like right here, it's like I'm just dealing with one object, and I could just bounce back and forth between the top and bottom without going into different objects for memory allocations. So, what else? And the one issue here that you might won't even realize about this bounding box renderable is that I'm combining the data structure and the rendering in the same object. If you're going to do this optimization really for your application or for your game, or whichever what you're doing, you don't want to do it this way. I'm doing this way just because I'm prototyping and because I will always want to see my bounding box. That is never the case for your application or your game. You don't want to see your bounding box. There is no reason to have the data intertwined with your rendering. Ideally, your bounding box should basically be a struct of some kind, or you can do like a very simple class, which just has the min and max defined, and maybe some other little bits in here, the little bits. Maybe you can have your bounding box, have the data, and then have a function in there that says, intersect ray, and then you can just pass in your ray object, and it knows how to handle that ray object to say, okay, it's successful. That might be a good way to do that bounding box class. Something simple that you end up applying like 100 times per scene, because you're going to have a lot of bounding boxes when you're dealing with a lot of objects on the screen. So yeah, so this is like I said, there's not really much to talk. It's like I just don't want you to take this as gospel. This is not really the best way to go about it. But for prototyping, and you don't want to make things complicated, then this is all right. You're just merging everything together because you're prototyping. You're just building. Like everything in Fungi is not the most optimizable best way to do something. Sometimes it's built for prototyping, really, to get the idea. Because ideally, I want myself specifically, Fungi is my prototyping platform, and then at some point I'm going to transition into desktop, and then a lot of these ideas will then get broken down into smaller pieces and then built as a real engine for desktop applications and mobile, whatever. So just keep this in mind. Like this is just prototyping ways of doing things, not necessarily the final. But like I said, if you're actually building something for real, separate the two. I think we've done this before with the skeleton meshes. I have skeleton data and I have a skeleton render. Like I said, that's the right way of doing it. Data and rendering should be separate, because maybe I don't need to render right away. I just want to handle with the data itself. And besides, maybe you want to have different types of rendering objects. You never know. It's better to keep the two separated. The data is always going to be the same. The way you render it can always be different. All right. So now I'm done talking. Let's really get some fun. All right. So we're going to bring in our bounding box, right? Everything kind of stays the same. We have our global object box. Nothing really changed. We just declare our box. We give it a default max and min, and we just push it to our scene. Very simple. On render, I think we don't do anything. On mouse down, we get our ray position. We draw a ray, and then we're going to start using our AABB test. So I have two examples. I have one with all the visualization, and then the one that's optimized, that's kind of mostly ported from the Scratch a Pixel website, because they have a really good bounding box algorithm, intersection algorithm. There's so many algorithms online. That's like the one I saw that I think that was probably the most efficient for use. That's why I'm using theirs. So now that we're in our test version, so we're going to get our direction of our array. So we have the starting point and we have our direction, or technically this will be its length because it's not normalized. So the length is also our direction. And you'll see that we're doing everything in the x-axis first, and then you'll see y and z. We're not doing everything in one go. The secret sauce, which I probably already got rid of the image. Undo, reopen. This one. The thing that confused the hell out of me is that they're doing x and y together. That's not what you're really doing. You're not doing x and y together and then adding z at the end. The way you code it, sometimes it looks like that, but that is not the case at all. What you're actually doing is taking all your 3D checks, right? And you're breaking your 3D environment, and you're breaking it down to a single dimension. You're only going to do x, you're only going to do y, and you're only going to do z. That's it. And then you kind of just take that data and then apply it in a certain way. And in a lot of previous examples, a lot of the previous videos, we've been talking about projection. Taking the length of like the length of one length and then applying it to our array so we can determine t. Like how far in our array do we go to find that t position on the array that actually does the intersection. This is the exact sort of equation. It is a projection equation, but it's done on a single dimension instead of 3 dimensions. So we're actually going to project, and you have to project it twice. You have to project the minimum value and the maximum value. So you have the start of our array, the x value, minus the minimum x by the direction of our x. And the direction of our x is, like, since it's not normalized, it's the grand total length of x. So for you to get an idea what I mean by that, if I'm shooting this, right? The minimum x is whatever x position this is. The maximum x, oh, actually, you know what? I'm talking about length. So the length, the length. So if I had this point and I have the endpoint, which is all the way down there, and I do a subtraction from endpoint to origin, I get the length of the entire thing. And it's not really the actual length. It's kind of like the offset value, the difference between the two. It's like how much x, y, or z and z does it take for me to get to origin to the end of this array? And I got the whole world flipped upside down to that array. So it's kind of like the length, it's basically the length of each dimension, x, y, and z dimension or axes. So by taking the length of x as the maximum value, you want to divide that length by another length. So if array direction x is the entire x length of that or the array that we're testing, we're going to take the start of that x and get the minimum, the shortest, the smallest point of that cube. Subtract that length, so we have that length, and divide it by the maximum length, and that gives us a fraction. So if somehow this value ends up equaling the exact same value as this, the division will create a 1, and 1 times our array direction would then be the endpoint. But that's not the case. Well, unless the cube is past the end of the array, because the array that we're using is not an infinite array, essentially, because we do have an ending. But the ending is really far. It's the end of our or projection. Our projection is like 1,000 units away, so it's the length should be extremely long. So we're just projecting the shortest the two distances. So like in this instance, if this is the smallest x, or the smallest x, actually no, sorry, this is a forward direction. So this is the maximum x, I believe, and this is the smallest x. So that corner. So I'm projecting this spot and that spot onto this whole line. Now, if you were to see how this looks in the single dimension, which is kind of hard to see with a projection, you can kind of see, you can't see because of the projection very well, but you're projecting this bound onto this lane, and you're projecting this bound onto here. So even though it's really far apart, this line is bound. It's like basically you just determined that in the x-axis, this is as far as the line goes, and this is as far as the line goes. So, but now you have to realize I'm shooting a ray through the cube on the z-axis, but I'm testing on the x-axis, right? Now let's say if I shoot this ray through the x-axis, I'm testing on the x-axis. What do you think you'll end up seeing? The perfect position of where it is. So on the first single test, if I'm testing on the x-axis and I shoot the ray through the x-axis, I already found my point of intersection. I'm technically done. Right? So that's I'm done. That's basically that is the point of the point of intersection. Now the question is, you might be like, well, why am I testing 2 points? Because if I shoot the ray this way, even though the points can be identical, one is actually better than the other. So the idea is that what you do is this gives you a ratio. It gives you some value, hopefully between 0 and 1. And if it's outside that bounds, then you really missed it. If it's less than 0, then the bounding box is before the ray. So like if I shoot the ray right here in front of the box outward, like I'm going to go step right in front and then shoot the ray. Let's see, can I now back up? That position is, that value is really below 0. It's like probably like -10. So if it's like below 0, that means the bounding box is before the start of our ray. So that's why you're kind of just checking between kind of 0 and 1, because this is 0 and at the very end is 1, because we're using that whole ray length as our bound. All right. So that's, so now you're like, okay, well, we do x axis checking. Technically you have to check all the axes, because if I shoot through here, the x is somewhere, right? Like wherever the x is like somewhere else. I have no clue where to go because there's so many red dots now. So yeah, it's really far, but it's still bound by the y-axis. It's kind of hard to tell. Yeah. Well, because I'm testing on x, that's right. If I was testing on y, you'll see it's bound. It's still bound by x, though. It's hard to tell because of the projection matrix, but it's still within the bounds of minimum and maximum. But even though that direction orientation is different. But yeah, if you go down this way, you can kind of tell. So, long story short, we're trying to project each axis onto the ray. And once we have the min and max, we have to check, is max less than min? Because it really depends on orientation. It depends on which direction the ray is coming in. Like I was showing you, if I'm testing on the x-axis, if I'm going from left to right, the value, even though if I go through the exact same 2 points, the t value is going to be different as if I'm going from right to left, different from left to right. So you have to check to see which one has the smallest value, because the t is the t distance, or the ratio of length from the origin. So the origin is different on both directions. So once we determine what is our two t values, our range, which one is smaller, and then we just do kind of a quick swap, and that's it. And the same thing is true when it comes to every single axis. If I shoot the ray through that specific axis, we basically get the value right away, right? So we have all three axes, and I gave each color a different, or each axis a different color. So you have red for X, green for Y, and blue for Z. So if I refresh one more time, if I shoot through here, now you can kind of see where everyone is. The blue is perfect. It's the two smallest values, and then you have all the other axis values. So that's the X test, that's the Y test, that's the Z test. So you basically have all these tests. Now you have to figure out which one of these points is the perfect point. All right. So you have you have 6 points of testing. And what you do is just do a couple of checks. That's all you got to do after that, really. Let's see. What is this one doing? So another part of the secret ingredient is that you want to get the greatest min and the smallest max. So as you go through and test, so right here I'm testing between T and Y max. If T and Y max, if the TX is less than TY, then the max X is the winner, because I want the smallest max and the smallest max and the greatest min. So if X min is greater than Y min, then we're good. And then we kind of end up doing the same over here for the Z axis. Since we have our T min and T max from our XY, or from our XY, that's where this image comes in. It's when you start doing those comparisons that this starts to make sense. But when you're kind of shooting the rays around, this doesn't make sense to me. So hopefully seeing it how it is in 3D world, and actually seeing the different axes, what the ray looks like when you go through each axis and during each test, you'll see that maybe this starts to make it look more sense. So that image is what this part is kind of all about. You're taking the X and your Y and trying to find, like, again, the greatest min, the smallest max. And then you take the what T min and T max is, and we compare it to Z. So you have TZ. If the Z min is greater than the current min, then make Z min our new min. If Z max is less than our current max, then make it our less max. So by the end, we have our greatest minimum and our smallest max. And ideally, if technically T min is our point of intersection, and you're done. So once you get to this point, T min is the best. I think there is another check you can do, but no one really talks about it. If you do other collisions, like sphere collisions, they talk about it, but they don't. I haven't seen anyone talk about it in the cube. If the ray is from inside the cube and you shoot it, T min might be 0. If T is, I think, 0 or less than 0 or something like that, you try to use T max as your value. Because now, if you're inside the box, T min is too small, and T max is then your actual intersection. But you're never shooting a ray from inside the cube, since that's why no one talks about it. But if you're making like if you're making something that's inside a cube and you're trying to shoot from the inside out, just take in mind that you probably should check for T min. If it's equal to 0 or less than 0, then T max is your actual point of intersection. So if I click save, now I'm using color 4. I think that's a gray color. So if I shoot my ray, gray color shows me our 2 points of intersection. And sometimes the trickiest thing, and especially when you're going through that, like you're going through every X and Y, Z axis and trying to get the, the maximum minimum, it's really to help with this too. If I'm shooting this right through the corner, I'm technically going right through every single axis. The green one is missing, so that means the looks like the which one is green? I think the Y test is probably what gives us the positive for both. So when you see everything through the axis, you see which axis you're testing at. That's the points that our team min and team max kind of like really align perfectly visually. But when you're going through all 3 axes at the exact same time, they all bundle up together. So that's why you kind of do that min and max thing too. It helps figure out which one is the correct one. So like see you have all our 3 axes together. Red is the X test of, let's see, can I? So think the gray is also our Y test. That blue is Z, X is red. So the smallest, let's just say this is the smallest min, right? That's the smallest min. That's the second smallest min. That's the third smallest min. Right? So during those 3 checks, those are the 3 min values you will have. But as you can see, the smallest min is too far. It's not even touching the cube. The blue, which is the Z test, is closer, but still too far away from the cube. But the Y test is the one touching the cube because it's also bound to the Y. Because this Y, like when you're doing the Y math, it bounds it to the min and maximum. So from here to here, it bounds it. So it can't go past that line. Hence why during this kind of intersection with going right through, this one is the one picked. But that's why I said the greatest min, because even though all 3 values are our min values, because we're testing with our X min or with our the minimum vertex, its greatest length, the one that's further away from origin, is the correct one, and you can see it visually here. And this is why you have that mix and man thing, and same thing over here. So you can visually see those if statements basically. That's our greatest, second greatest, and least greatest. And that's what we're saying. We're trying to get the smallest greatest. And again, that's the smallest greatest. It's the one closest to origin. So if we're doing maximum, we're trying to get what's the closest to origin. And if we're doing it from the minimum side, we're trying to see the ones the furthest away from origin. So like I said, this is how you can see it visually. All the math and all the if statements. And that is the gist of a bounding box. Hopefully this makes much more sense than trying to understand it in a one or two dimensional way. I think seeing things visually in 3D and seeing how everything actually is makes more sense. Like to me, this makes perfect sense. Seeing the if statements. Now I understand why I need the greatest min and the smallest max. It makes sense now. And I see where the numbers are. It's like, oh, okay, that makes total sense. And everything's kind of bound to its specific axis. Like X is bound within its axis. Z is bound to its axis. And then the green, which is gray because that's the successful point that we found, is bound to its Y axis. It's like everything's below Y because those tests aren't bound to the Y-axis. They're bound to their specific axis. And so by the time we get to this position, it's like that's the one. That's the spot we need to be at. So that's our test. That's our visualization tool. Now if we go into our other function, which, like there's some, I forget which YouTube video, but these things probably explain the math. They explain how to do the math. I'm just trying to explain it in the visual way. Now here's a more optimized way. All the visualization things are taken out. The testing on the X and Y, Z plane is done early, so we don't have to do Z. So if Tmin is less than max or min is greater than Tmax, return null. It's one of those checks you can do to kind of end the intersection early. And then you can do Z. So basically you kind of do X and Y first, and then you do Z secondly, just like what the image from Pixel, Scratch Pixel tells you. So their image illustrates how you program it, but it doesn't illustrate really well how the math works, in my opinion. But that has nothing to do with them. That's pretty much how I think everyone's taught. Everyone's taught to see it that way because it is a one-dimensional thing. Like I said, each person is different. I'm a more visual person, so even though that image just doesn't radiate well with me to understand it. But hopefully seeing that image and seeing the 3D way, hopefully all this starts making a lot more sense. Especially if you start reading into it. Like, I really suggest reading Scratch a Pixel and maybe watching that, whatever YouTube video this is. I forget. I feel bad. This might be the programming. You become professional. Yeah. George Rodriguez, definitely a go-to YouTube channel to learn a lot about mathematics for game development. So yeah, he goes through the math, and he also does it with the whole X and Y dimension only. He goes into depth a little bit, but again, you're stuck trying to understand how it works in 3D in a two-dimensional space, and I had to watch this video several times to try to understand it, but whatever. That's the whole point. Once you take those two references, take this video, you have this well-round, 3 points of perspective of how to understand something. So let me just finish explaining how this function works. This is our original that we were doing in our test. We're doing everything this way, all right? We're just doing our bounds testing or our projection on the single axes or whatever. But we're doing division. Now, in an environment, in a game or an application, you're going to do tons of tests on bounding box. So if you have 50 things on screen and each one has a bounding box and you have to test all of them, division is one of the slowest operations you can do. So one optimization thing you can do is to take away the division and make it a multiplication. Now, the way to do that is that you kind of make the inverse of the value. And the inverse of the value is just 1 over x. So I say 1 divided by x, that gives me the inverse of x. So by doing that 1 divided by this, I can take that value and then just do a multiplication. And you end up getting the same value. So dividing by this or multiplying by 1 over x gives you the same result. So that's one optimizing thing you can do. Now, the thing is, you have to. Now you want to check basically. You want to take away this if, or now you have this if statement, right? And this if statement does a swap. So if you want to take away this swap operation, you can kind of do it like you have an if statement and then you have a swap. What you can do, since you have this inverse, if it's greater than 0, then the smallest value is going to be is going to be the min, the min part of our bounding box. If it's less than 0, maximum is actually going to be our smallest value. So this way, by having this one if statement, we kind of just get rid of this whole swapping thing, and we do the math and put it into its proper variables, just exactly where they belong. So we kind of simplify this a little bit. It looks more complicated, but we kind of take away one operation. We take away one variable, and we take away a swapping operation. Scratch a Pixel has a really cool idea where you check the values, right? You do this if statement once, like not inside this function. Ideally, you should have like a struct for array, and in that struct array, you'll probably have this bounding value, like that intersection bounding value. So this way, you can kind of speed things up along. So you do this if statement for every single axis, and you save the value 0 or 1. Like if it's less than 0, then the minimum is 1, right? No, minimum or the maximum is 1 and whatever, and 0. So and then once you have that kind of that range, and then you use that bounds, like I said, in the bounds, I saved it as an array, so you have vmin and vmax. If b equals, let's say x is greater than 0, so we get back the value 0. So once I'm in this if statement, or not really an if statement, this is really an array, and I'm putting in the index, I'm going to put the value 0. So I'm going to get the t min, or the v min value of x. So if that's 0, and if I say 1 minus 0, I get back 1, that means I'm going to get the max, the v max x. Now, if x is less than 0, I'm going to get 1. So here it's 1. So for t min, I'm actually going to get the v max value for subtraction. If that's 1, so 1 minus 1 equals 0, then I'm going to use v min. So by using this, by doing these quick if statements and then saving the index between 0 and 1, if you're doing this like in a loop of 50 or more, you basically get rid of this if statement, and you get rid of the swap, and you reduce it all into just an index retrieval. That's all you do. So you take away two big operations, and you do this. So this ends up becoming something called branchless. It's not really completely branchless because you still have if statements, but this whole operation is no longer branch. It doesn't have an if statements at all anymore, because you do the if statement once and you cache its value, and then you reuse that value for all your bounding tests. And you just continue on, and you just do it for each axis. And that is Scratch a Pixel's optimization tricks for bounding boxes. And this only works for axis aligned bounding boxes. This optimization trick doesn't seem to work for object aligned or oriented bounding boxes. Those boxes can rotate. And that's what the next video is going to be. It's going to be about OBB, because this video is all about AABB, axis aligned bounding boxes. And if I click save, oops, refresh, reload. Now anywhere I shoot my array, it's going to show me the exact point of intersection. I'm going to shoot it down that one. It's perfect. Shoot down that. Whoa. Shoot that one. It's perfect. Shoot that one. It's perfect. Shoot up. Perfect. And you shoot down. Perfect. And the end. That is our bounding box intersections on all 6 planes of the cube. And that's it. And that's it for our video. So this is axis aligned bounding boxes. Next video we're going to be able to talk about object aligned or oriented bounding boxes. So the box will end up being rotated, and we got to do a couple extra steps because now we kind of have to figure out its directions. Because right now, that's the magic trick to access a line bounding box, because we know where it's forward, its right, and its up directions are because they're aligned to the axis. Once you start rotating, those directions, they're unknowns, and you have to calculate them. So they take an extra step. So that's why usually when you read about like optimization, no matter what object you use, you will always usually want to test axis line bounding boxes first, and then then you can probably do AABB tests, because that takes more math to do. So it's like when you're testing all the objects on a screen, you do all the AABB ones first, and then when you find it, then you do the secondary tests, because then just to make sure that's the object you actually hit. Like when you're dealing with a capsule, you might end up grazing it, the capsule, so it might not be considered successful. Then you go to the next object and do the bounding box, and then you check that capsule, make sure you didn't graze it, in the top part. Because, like I said, the bounding box is a different shape as a capsule. A capsule, you can kind of still get through it. So, yeah. So, like and subscribe, and see you guys at the next lesson.